Okay, welcome. This is the first lecture of Algebra 1 Honors, Basic Set Theory. But since it's the first lecture, I need to explain a couple things about the course in general, the nature of the course. So all math is really based on simple ideas. And I want you to imagine that you actually don't know any math. And if you don't know any math, where do you start in a math course? Do you start with just adding numbers? Do you start with maybe go back to just counting? Well, in math, no. That isn't going back far enough. We have to be even simpler. So we're going to start with some simple ideas today. And eventually these simple ideas are going to lead us to some more profound ideas that we discover. So through the simple, we discover the profound. Now, how do we communicate these simple ideas? Well, you could use words and paragraphs and essays to discuss the same ideas that I'm going to mention today in set theory, but it's not an English class. And also, if you use lots of words, it takes longer to read. So we're going to use symbols. So ideas, symbols. We're going to use the symbols to communicate these ideas. And that way it won't take forever to communicate these simple yet difficult to convey ideas. So the first idea is the idea of quantity. Math is interested in quantities, right? All right, and there are different quantities, but some quantities, say the numbers 2 and 4, they have things in common, right? And then other quantities have things in common that are not obvious. Maybe 2 and 7, they have something in common. Or the number 37 and 62, they may have something in common, but it's not obvious. But if you have different things in common, that share common characteristics, then you can start talking about what these quantities have in common and discuss what are these characteristics, why are these characteristics important, or maybe they're not so important. So this is the whole idea behind set theory. Set theory is the study of quantities that share common characteristics or share a common usefulness. So we're going to start with a little bit of vocabulary so that when we discuss these things, we all understand what everybody's saying. So first we have the idea of set. What is a set? And I don't want to get too specific, so I'm just going to say it's a collection of unique things. A collection of unique things. And then I'm going to call the things elements. So elements are the members of a set. What if I only want to talk about some of the elements in the set and group that smaller group of elements from that set and just focus on that group? Well, I can call that a subset. a subset is a set that is a portion of I'll say a previous set, a set that you already know about. What about a set that doesn't have any elements? Can you have a set without any elements? Sure. For the sake of argument, we're going to create something called the empty set. A set with no elements. Well, there's something simple about these sets I can discuss, and that is how many elements there are in each set. So we have a word for that. Cardinality, which is the quantity of elements in a set. Okay, we just have two more, and then we can get started on developing these ideas. Equivalent sets. Sets with the same, I'll underline that, same cardinality. For example, if a set has 3 elements, another set has 3 elements, they are equivalent. Well, what about sets that are exactly the same? We call those equal sets. So I'll define that as identical sets. Okay, so this is our first set of vocab, and this is all the vocab we need to develop all the ideas in this first lesson. So I'm going to create for you an example of a set. So I'm going to create a set called capital A, and I'm going to put these 3 elements in the set 1, 2, 3. And you know they're in set A because it says A equals, and then I have the 3 elements, or any number of elements I choose, inside the braces here. So, since this is telling me that capital set A contains the elements 1, 2, 3, then I can say some things that are true about set A. For example, I can say that number 1, the number 1, is an element of set A, and in symbolic language, that's how I write that. 1 is an element of A. I can also say 2 is an element of A. I can also say 3 is an element of A. But 4 is not an element of A. And I write that by writing the same symbol I wrote before, but a slash through it. So that is not an element of. In general, in math, when you put a slash through something, that is how you express not in any situation. Okay, now what about subsets? I mentioned that a subset is a portion of a set, and sometimes I want to talk about a portion of a set and not simply just one element in a set. So I can take a portion of this set, for example, 1, 2, the set containing 1, 2. Now I've created a subset of set A. And I can even tell somebody that this is a subset of set A. So I'm not going to use element of, I'm going to use this to state that the set containing 1, 2 is a subset of set A. This is also true. 2, 3 is a subset of A. This is also true. 1, 3 is a subset of A. Okay? It is also true that 1, 2, 3 is a subset of A. So in case you were wondering, can a set be a subset of itself? Yes. A set can be a subset of itself. But what if I only want to talk about the sets that are parts of set A and not, maybe I don't want to include this type of subset. So we have something called a proper subset. Whoops. Proper subset. So a proper subset is never the set itself. It is a subset, like these are subsets, but we're excluding the set itself. So proper subset is always smaller than the set itself. So if I were to list these 4 subsets of set A, and then I asked you which are the proper subsets. The proper subsets are this one, and this one, not this one. Okay. Also, it's also true that this is a subset of A. So is this, and so is this. So a set doesn't have to have more than one element, it can have just one. And as I said, a set can also be empty, which leads me to this question. This is the empty set. Is the empty set a subset of A? I'll put a question mark here. What do you think? It doesn't have anything in it, so can I say that it's actually a portion of A? The answer is yes. Here's another way to write empty set. It's just synonymous with that. Empty set is a subset of A. Because if I take the empty set out of A, I'm not changing it at all. If I superimpose the empty set on top of A, that also doesn't change A. That's a test to see if something is an empty set of it. Okay, in the vocab I mentioned this, cardinality. Remember, cardinality is just the quantity of elements in a set. So we have a symbol for cardinality, and that is lowercase n. So if I wanted to express the cardinality of set A, and remember A has 3 elements, I would write lowercase n and then in parentheses set A equals 3. Okay, I'm going to create another set. Let's make it 1, 3, 4, 5. This set obviously has 4 elements, so the cardinality of B is 4. It has one more element than set A, which means the cardinality of A is not equal to to the cardinality of B, right? I could even be more specific. I could say that the cardinality of A is less than the cardinality of B, right? Okay. And what about the cardinality of empty set? Well, it doesn't have any elements in it. So, cardinality of empty set is 0. Okay, finally, we come to the idea of equivalence. When are two sets equivalent sets? Okay, so let me reiterate what set A had. 1, 2, 3. And I'll create a new set. Let's make it 2, 4, 5. We'll call it set D. These two sets both have, I'll write down the cardinalities. Cardinality of A equals 3. Cardinality of D is also 3. So A and D are equivalent. I can also write cardinality of A equals cardinality of D. Now, I cannot say the following. I can't say that A equals D. No, I can't say that because A equals D would imply that A and D are identical. They have not only the same number of elements, but the same elements, and they obviously don't. If they did have the same elements, I would call them equal sets. It's kind of trivial and ridiculous, but if I had set A 1, 2, 3 and I had another set called B and it happened to have 1, 2, 3 also, then I could say this, that A and B are equal sets, A equals B. But I can't think of a situation where you would have identical sets. It doesn't mean that you won't see it at some point, but it's definitely not common. But let's go back to the idea of equivalence. Suppose you had two sets and you didn't, let's pretend you're not able to count. Okay, so you can't count. You've forgotten all your numbers. You can't count. You don't know how to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if you're given two sets and you were asked to tell me if they're equivalent or not, if they have the same cardinality, how would you do that if you did not know how to count? Let's say you don't even know the names of the numbers. Any numbers. Well, you could do what a little kid does, and that is match up. Match up. I'll use sets A and D as examples. So this is A, this is D. And remember, I don't know how to count. So I can't go 1, 2, 3, 1, 2, 3. Aha, they have the same number of elements. I don't know how to do that anymore. I'm a little kid, I don't know how to count. But if I ask a little kid, which one has more? Which one has more? Then in his or her mind, he might pair up the objects in each element like this. There's a pair, there's a pair, there's a pair. And there are no more elements left out here. So, A and D have the same cardinality. They are equivalent sets. Now, what would happen if they were not equivalent sets? Okay, I'll make us a new set called E, and let's just make it 4, 5, 6, 7. And I'm going to do the pairing up again. Uh-oh, there's one left over. that must mean that set E has more. So they don't have the same cardinality. Okay, in math, now I'm going to throw out another vocab word at you. In math, if two sets can be lined up and paired, and the elements in both sets can be paired off like this, such that there's nothing left over. This is called 1-to-1 correspondence. These two sets, A and D, are in 1-to-1 correspondence with each other, because for every element in A, you can find one in D to pair up. Over here, you can pair up almost all the elements, but there's something left over. So these two sets A and E are not in 1-to-1 correspondence, not. So if two sets are in 1-to-1 correspondence, they are equivalent. They have the same cardinality. If they are not in 1-to-1 correspondence, they do not have the same cardinality and therefore are not equivalent. Okay, I'm going to end the first lecture there, and we'll continue with these ideas of equivalence and cardinality next time.